Hi, so today I thought we're gonna look at the animation and instancing workflow with the infection solver. This is updated late September 2022, and if you don't have the latest version, please go to our GitHub and download it. Also on the GitHub you can find our wiki page, which is quite nice. We have quite a lot of info here. So if you go to like microservice here, you can see a list of most of them has been updated, and we have small GIFs for some of them that shows how stuff works, which is quite cool. Some haven't, some is just like a little bit basic text, but lots of them have like examples and how it actually works. And you also have like list of all the attributes that so you can see what they do and stuff like that. So that's quite useful. And of course on the GitHub page you can just download the project. You don't need to do anything. You don't need to sign up for GitHub or anything. You can just download the OTLs if you want to. Great. So yeah, let's get started. What I'm going to do here is I'm going to do a simple infection, and then I'm going to copy some tubes to it, kind of. And we're going to look at primarily the animation and copy tools. So I'm just going to drop down a grid, and let's just sketch some point on this grid. So what I'm going to do is actually going to scatter quite a lot of points. I'm going to scatter 400,000 points. And the reason I'm doing this is not because I want 400 copies, but rather that I want the structure to be kind of cool, and for that I need some points. So after that I'm just going to do infection initialize. That's good. And I'm also going to do a sphere that I'm going to drive that infection from. So if we highlight this, we can see, and what I want to do is I want to move this a little bit upwards to start, and I'm going to make it a little bit smaller, 0.5, and then after 24 frames I'm going to move it down to 0. It's going to keyframe that, so we have a cool animation there. Great. So what we can do now is we drop down a dot network here. So in the dot network we can drop down an infection object, and in between that and the output we of course want a solver as well, so we're going to do infection solver, and what we have now is this, and it's just black because we don't have any density yet. We can do a visualization, bring this down to 0.15, so we have a little bit smaller particles. I'm going to emit from geo, going to plug that one in, and I'm just going to choose our little sphere here, and instead of contact I'm going to do point base, I'm going to do inside, and I'm going to bring up the density emission to 25. So what happens now is this goes down and it emits, yeah, and nothing more happens, which is quite nice. What we want to do here as well is that we want to bring up the fuel to maybe 1.5, and that gives us the option of actually going over the density and growing out a little bit. You see here that now it actually grows a little bit outwards as well. And this is needed for the curvature avoidance, because it doesn't inject velocity, it only grows where there already is density. So we're gonna drop down the curvature avoidance top, plug this in, and I'm just gonna tweak this so it gets a little bit sharper. And I'm gonna bring up the amount to 25, which equals 1 point of density per second. Per frame, because I have 25 frames. So something is happening here. It's not super funny. It's quite dull, I would say. So what we want to do is we want to maybe have this a little bit sharper. And what I want to do is I'm going to use some movement amount, which actually inject a little velocity. And I'm going to bring down the threshold, which makes it a little bit sharper. So, and what I also want to do is I bring down this tag, and the tag just adds a note on the point when it has reached a certain threshold of density. So I'm going to put this on 0.5. And what this will do, if we just check here, now that some are infected and it starts growing. So what's happened now is that the ones that have reached 0.5 of density now have a tag. So what we see here is they have a tag is one, and it also says when they're tagged, and then is then used to drive the animation. So this is often important if you want to do animation. You can also do animation based on density, but I think the tag is a lot better to use. So here we go, we have something that looks quite cool. Let's keep this at 100 frames or something. So we have 100 frames here. And what we can do now is we can step back here. So since we have a tag, we can use the tag split here. And what the tag split gives us is three outputs. The first one is newly tagged particles. And the threshold here says how long ago they can be tagged. So this is in frames. So now we have this been tagged 10 frames ago, 1 frame ago. So that's that. And if we look at the middle one, we just get the dead particles, so to speak, non-tagged particles. So these are all the particles that hasn't been tagged yet. And in the third output, we get the particles that have been tagged, but is outside this threshold. So the older tagged particles. So to get all the tagged particles, we can just merge the first and the third input, and that gives us all the tagged particles. And yeah, now we have a bit too many points here. So what I want to do as well is I'm just going to do a little bit of X code. So what I'm going to do is I'm just going to do a wrangle, and I'm just going to say if I at ID, which is the ID given by the solver, so it's constant over time. It doesn't change with the point count. And then I'm going to do a modulus function, which actually says every 10th or 20th, so let's say 10th of the ID. If like what I say here is that every 10th particle is not 0, which is basically just counting up, and yeah, you have to Google modulus function. Sorry. Then we just remove it. So basically what this does is it removes 90% of the points. So we have this. And what that gives is we still have the structure that we could get from the solver, but we have removed a lot of the points. So that's cool. Not super cool, but yeah, who knows. So what we're going to do now is we're going to drop down the animation node. And let's plug this in. So what we get now is kind of nothing. The default here method is using tag. We can change it to density instead. Doesn't really show anything as well, but if we start outputting p-scale here, we will see it goes so fast, but you can see here that it actually grows as the density grows. But if we rather use the tag instead, it starts growing when we have the tag, and that way we can control the animation length. So we can have an animation of 80. So we can also do it less, taking it down to like 10 and 5 frames random. And what you will see, we have a very fast animation. And if we bring this up again to maybe 25, you can see with this ramp also affects it. So if we do, slowly in kind of thing going on, you can see that we had something that looks like this. So it's slowly and then it's faster moving in. So you have this control. And what this does is that it affects both the p-scale as well as the animation attribute. Animation. So we have animation right now that is normalized. So by changing this, we also change the animation attribute. And when it comes to p-scale, we also have the option of randomizing the p-scale. So we can set the general scale here, and then we can randomize it as well. So right now it's not randomized. And we have a min and a max here as well for the random thing. So we can do 0.2 and bring it down so we don't get anything lower than that. So that's like a low and a high clamp. So that's good. So let's talk about the animation attribute. As default, we put out an animation attribute that is normalized. We also have the option putting out a frame animation. What it does then is just counts up from when it's tagged. And it counts up towards this. So the furthest it can be now, because we have an animation length 25 with a random of 5, then it counts up. And all of these can then be used in the infection copy. So if we put down an infection copy here and plug in these ones here, and we do something very simple, we put down a tube. So a tube here. Let's move it up so it sits on Origo. Let's add end caps. Let's bring it down to 5 columns and 20 rows. And let's twist it. Let's do a twist. Let's start off with a lot of twist. Oh, let's set capture region first, of course. So capture region should be 0, origin 0, direction 1, length of 1. I guess it's good. Yeah. So let's say we have something like this. Let's do the tube small towards the end. Yeah. And let's say that after 48 frames we have 0 here. So we have animation that looks like this. Oh, not very fancy, but yeah, that's what it is. So if we were to put down a copy and put this down in here, what we get now, we get kind of small things here. So what we could do is we could bring up the P scale and let's see what's happening. We see that they turn up, but also we have a problem that our animation right now is 30 frames, while the twist here is 48. So what we need to do then, if we want to use the frame animation, we need to bring this pretty much up to 48, and we can't hardly do. Maybe we can do if we bring it up to like 53 and have 5, that would work because it can't go under 48, and that will give us something that's actually the same amount. So we have this, but then again, it's kind of unclear, and the problem is that the P scale is the same length as the animation. So if we do another inflection animation and we remove the P scale here, so we can skip P scale information here, but just do P scale information here instead. So we do output P scale animation, and we can make this shorter, maybe make it 10 with a 5 of random, and then we can keep the ramp as it is. What we have now is we store this P scale information up here, and then we just do the animation settings here, which in turn will give us something that's animated fast, and then it turns slowly. And maybe we bring up the P scale to something 0.5 instead, so we actually see what's going on here. So what we have now is this. We have something fast, and then it continues to move, but it's quite weird. I guess I'm gonna see what's going on here. So let's look at animation here. Oh, we have, what the fuck's going on here? Oh, we need to change this because we need to do this linear, because otherwise it looks weird. Let's look at ID as well. Yeah, it seems to be working. Yeah, so now we have this going on. But what we rather want to do when we do things like this is to we don't really want the randomness, and we want this very linear, which is kind of bad, so boring. But if we do this, it works a lot better. So it's just, yeah. But what we could do instead is we can skip the frame animation. We can just do floating frame. And what that gives us is the option down here to actually say how long the animation length is. So if you say that this is 48 in, what we can do now is we can set it to whatever we want up here. So if we go back here and we say animation 10 with 5 random, it will still keep that. So it goes really fast now, so we can hardly see it. Let's bring it up to 50 then. So now we can control the animation based on this instead. And we can do whatever random we want. We can do 25. So we have a very random. And what we can do is we can also use this kind of, we can also use the ramp quite well, because this is all just normalized. So now we have something that goes very fast, and then it just slows down. Yeah, you see it's moving very slow towards the end. The problem with this is that it's a lot slower, because now we iterate it over each point instead of doing it over each frame, which we do to frame animation. So this is quite a lot slower, but it gives you more control, and it kind of looks better, I think. And what else do we have? If we were to go back and maybe do something more interesting, so we have this grid, and we put down a mountain. We give it a little bit more. We give it 250 rows by 250 rows, and we do a mountains up here. And put down this, Let's just bring up this size to 10 or 5 maybe. 3, so we have something that's a little bit more random. And before we scatter, we're going to put down a normal. We could do whatever kind of normal we want, but let's just do a point for keeping it simple. Do a point normal, and now we have normals on the scatter. So we go to the infection solve again. It doesn't change that much. It will probably look the same. Yeah, it will, kind of. Sorry for that. So here we have the animation, and what we could do now as well when we do the copy here, we will just have these and they turn because we have normals now. So let's just do a transform on this. Transform it 90 degrees. Is it 90 there? Yeah. So what we can do now on the animation here is we can also do output orient attribute. Oh, then we maybe should remove that again, sorry. So what we can do here is we can also rotate it around the normal, etc. It's not very clear with this kind of thing, but if we were to do something, yeah. What you can see here is we get this kind of rotations. So that's quite good. And you can do this without normal and try to estimate the normal, but I think it's better to keep this, have normals with it. So you also have that kind of option. And yeah, I think this is, I mean, depending what you want to do, either use the frame animation to have something fast. You see it's so much faster, it's literally, but with very limited amount of what you can do because you can't really handle the frames, or just use the point to get quite good complex animation. So yeah, that's pretty much it for this, and thank you for watching. Please follow on GitHub and stuff to get latest updates, and hopefully I will get something that supports packed alembic and packed animated disk primitives, whatever. Animated disk primitives, I don't know, sequence disk primitives, whatever, soon. And that will make it a lot faster as well. Thank you, bye.